spectrum as well as the portion of X-rays in spectrum that is generated by laboratory X-ray source. Then we will also discuss in short basics of crystallography, because X-ray diffraction is used to understand the crystal structure of any material. So first of all, we have to understand the nature of X-rays, then we have to understand the basics of crystallography, and then we have to understand the interaction of X-rays with crystals. So then we will also learn how to monochromatize X-ray from X-ray beam, because in X-ray diffraction mostly monochromatic X-ray beams are used. Then we will see the fundamental or basic law that can govern this X-ray diffraction. That is Bragg's equation we will deduce in very simple manner. So you need not have to do very complex calculations for it. From trigonometric relationship and the equations of parallel lines, we will understand very easily how the Bragg's law can be deduced. Then we will see the importance of X-ray diffraction. So we will first of all see the characteristic of X-ray diffraction pattern, and then we will see the importance of peak positions in this XRD pattern. Then we will also discuss in short the intensities shown by all these reflections. There is a variance in the reflection intensities. So we will see the parameters which determine the intensity of each peak. Then we will take an example of cubic crystal structure, and then we will record powder XRD pattern. So I have some software where you can theoretically calculate X-ray diffraction pattern. So we will calculate the pattern and then we will analyze it, interpret it by using a simple calculator. And then from those data, we will see various applications of powder XRD in this particular session, and the specialized applications I will try to cover in the next session. So in the first lecture, we will see the fundamentals and very primary applications of this tool. Before starting my lecture, I just want to remind you about the story that everybody might have listened in their childhood. So at certain time we used to listen the story of elephant and 5 blind men, because we during your coursework you have to learn so many techniques, but nobody tells you okay which technique you should actually know for your material. So because it is a logical thing that you have to gather the information that you know about your sample. So accordingly, you should choose the tools that can address your material very clearly. So this story, we know the story. Now it is time to understand the moral of the story. So you know that there is an elephant and 5 or 4 blind men describe these elephant. Somebody says it is like a trunk. Somebody says it is like snake, or somebody says it is like a sheath of leather or like a broom, something like that. But at the end, nobody is wrong at their position, because this person, whatever it is there, he has touched the ear of the elephant, and whatever he experiences from that touch, he explain about that particular matter. So you need to gather the information. So if you gather the information that is collected by each individual, so you can address this elephant more, we can say that clearly, than the information that you get from individual. So who is correct and who is wrong is a question. But at least at the end, there should be, we can say that truth can be addressed in different ways, but at the end, there should be harmony. So otherwise there will be dispute or conflict of interest will be generated. So good example, this particular story is a good example of resolving the conflicts to have harmony with the others who have different viewpoints. Because if you characterize TiO2 by visual spectroscopy, you can only understand that TiO2 is a wide bandgap semiconductor. If you characterize TiO2 by TGDTA technique, you will understand that there is no weight loss from room temperature to 800 degrees centigrade. So certain information you get from each and every technique. At the last, if you collect all sorts of information together, you can address your system very clearly. So you have full of knowledge or information with you about your system if you use different tools to characterize your system. So different techniques are required to describe the same system more precisely and accurately. This is the moral of the story. Now we will turn towards the X-ray diffraction. There are so many techniques, instrumental techniques that we use to characterize our material. Generally, powder XRD is the technique that we use to define a structure of polycrystalline material. Polycrystalline material means, so if you take single crystal and crush into powder, that crushed powder is nothing but the polycrystalline material. That is also crystalline, but it is not a single crystal. Now it is converted into thousands of crystal. So powder XRD is the technique that is used to determine the structure of polycrystalline or powdered crystalline materials. Why we need to understand the structure of material? The question of this is underlying behind this particular quote. Structure and property are intimately, finally related to each other. So if you change the structure, property will change. So structure and properties are intimately related to each other. Therefore, it is of paramount importance to understand the structural properties of the material. So if you understand the structure, that you can link the property with that particular structure. If you can change the structure, properties will be definitely getting changed. So you can design a material in a such a way that you can tune the structure of the material, or you can modify the structure of your material so that you can design a material with enhanced properties. So this is the beauty of this technique. So if you understand the crystal structure, and if you understand link this crystal structure with its property, and if you want to improve the property, you can monitor the structure. You can just change it, you can dope something, or you can just have different phases of the same material so that you can get improved properties. So this particular technique is used in so many industries. We will discuss them little late. Now we understood the importance of powder X-ray diffraction tool to characterize the materials. Now it is a time to move to discuss the nature of matter. The nature, the states of matters, we can discriminate the matter in three different states that we can experience normally. So everywhere we can see the gas. So matter can be present in the form of gas. Matter can be present in the form of liquid and solid. Now this tool of X-ray diffraction is only applicable to solids. If you want to characterize the liquid material, so it is not possible to use X-ray diffraction tool unless until you can play a trick here. You can condense this liquid material, you can just crystallize it. For example, water, you can convert it into ice, and then you can understand the crystal structure of ice. But if you solve the structure of ice, and if you want to correlate the properties of ice for the water, then it is very difficult, because the properties of crystalline water, that is ice, will be different than the liquid water. So there will we cannot establish a link of properties of water from the structural data of ice. So the next part is that solid material, gas cannot be also characterized by using X-ray diffraction technique. Among the solid, 95% materials are crystalline, 95%. So whatever solids you can see around you, among those solids, 95% of solids are crystalline. And only 5% of the solids are amorphous in nature. Glass is best example of amorphous material, while crystalline material, you can take a chalk powder, eggshell, if you will crush it, and if you will take powder of eggshell, crushed sugar, you can use the X-ray diffraction to characterize. You can use the X-ray diffraction tool to characterize the crystalline material. Now our focus will be on only crystalline material in this particular lecture. So if you will expose crystalline material to X-ray diffraction experiment, you can see well-defined XRD pattern that is resulted from the experiment. So x-axis you have to take 2 theta degree. What you have to do, you have to change the angle of incidence continuously. That you can do by using goniometer. I will explain you at the during the lecture. So first of all, you can just look into it. The crystalline material will give out well defined XRD pattern. If your material is a monoatomic gas like nitrogen, Cl2 or something, hydrogen, something like that, oxygen. So the monoatomic gases will not show you. It will change the angle of incidence of the sample with the incoming X-rays or incident X-rays. So there will be only scattering. So no peak will be there in the pattern. So this is, we can say that, speciality of the gases when they interact with the X-rays of single wavelength. If your sample is amorphous in nature, amorphous like a glass, or you have amorphous silica, sometimes your materials are disordered amorphous materials, then the XRD will produce we can say that this is a big hump, or you can call it as a diffuse peak. When you subject amorphous material or liquid material to X-ray diffraction experiment, you can see hump or a diffuse peak that will start from 20 and will end almost up to 30 or 40 degree to theta values. And if there are some spikes over it like this one, so you need not have to call it as a peak. So this is your noise of detector. So somebody will put HKL values over here. It is very, we can say that. So you are very brave if you will do that. Okay, these are the peaks and all those things. So before indicating any HKL value over these particular peaks, you should understand the definition of peak. Okay, now at this moment, X-ray diffraction of a crystalline material will give you a defined, well-defined X-ray pattern. So we will now go into the details of this pattern. So now we have understood the properties of metal, so solid, liquid and gases. So among the solids, 95% solids are crystalline, and we will use our tool to characterize this crystalline technique, crystalline solid. So solids, we know different types of properties are there with the solids. Solids are having definite shape, definite volume will be there, that is possessed by solids. There will be definite mass that is associated with the given solid. Intermolecular distances or interatomic distances present in the solids are very short, because the atoms are tightly packed in a short. You can see that this is a solid, this is a crystal of sodium chloride. So chlorine and sodium atoms are packed very closely. So close packing, packed structure is present in the crystalline material. So intermolecular forces are very strong. Their constituent particles, atoms or molecules, have fixed positions. So their constituent particles have fixed positions and can oscillate about their mean position. So solids are incompressible and rigid materials. So the atoms are closely packed. So there is no empty space present in the solid. Close packing is there of the atoms or molecules which make the makeover of that particular solid. Now we will see amorphous. We will discriminate first. You can see that first application of X-ray diffraction is that you can go back to this particular slide. If you don't have any knowledge about XRD and if you will get XRD pattern of your material, you can at least know the first application of X-ray diffraction is to differentiate your material into either crystalline or amorphous. So if your material will give you this kind of XRD pattern, you can confirm that your material is crystalline. If you get diffuse peak ranging from 10 to 30-40 degree, so if you will get a broad peak like this one, we call it as a generally hump. So if you will get this kind of peak, and don't bother if there is something like this, some wavy signals are there, you just forget about these signals. These are not peaks. So this particular hump will tell you your 95% material or 99% material is amorphous. So first application of X-ray diffraction is that you can discriminate or differentiate your sample into either crystalline or amorphous by using this tool. Now we will go back to the solid again. The amorphous solids. So what make this amorphous solid to give the diffuse peak and what make the crystalline solid to give a well-defined XRD pattern, we will see now. The atoms in amorphous materials are arranged in a random way. Random way means, for example, if you will see the ground flooring, so you will have tiles. For example, 2 by 2 tiles are there. First tile, then there will be next tile of the same dimension, then third tile will be there. So this is a repetition. Ordered repetition is there. So after each 2 feet, there will be a new tile starting like this. So we call it as a ordered or repeated pattern of packing. But if you will have random way, so the next tile will be placed like this. So this is random orientation. So the next one will be something like this. So this is a random packing. There is no regular order of repetition is there. That kind of material is called as an amorphous material which has disorder in packing. So the same disorder is found in the liquid. If you take glass as an example of amorphous materials, so glass, so most of the liquids are amorphous in nature and we generally say glass is super cooled liquid. You might have read it somewhere. Glass is super cooled liquid. Now, if we consider liquid, there should be fluidity. Super cooled liquid means the liquid which is suddenly cold. So, if glass is super cooled liquid, the glass should show fluidity. Means like a liquid, glass should also have some kind of flow, but that flow is very slow. If you place your glass panel in upward down direction for 100 or 200 years, so the base of this glass, the breadth of this particular base of the glass will be enhanced. So this has been observed in European countries. So there were some window panes. So after 100 or 200 years, it has been found that this particular base is enlarged. So because of the fluidity of this particular liquid. So amorphous solids are having random arrangement of the molecules or atoms within their structure. So we cannot study them by using XRD. Crystalline material. So the crystalline materials are the materials in which the atoms, for example, sodium chloride is a crystalline material. Now sodium and chlorine are the two types of elements that those are present in the sodium chloride. So you have sodium atoms, you have chlorine atoms in the crystal structure of sodium chloride. These atoms are arranged in a regular pattern, and there is a smallest volume of element that is, it seems to us that it is repeated in three dimension. So the smallest volume unit, whatever it is there, for example, if you consider this particular repetition, so if you want to understand the structure of this particular object, you have to only solve the structure of this particular unit, because it is only repeated in this direction. So if you repeat it in this direction or three direction, it will make over the material in 3D. So in a crystalline material, there is a smallest volume unit. So that seems to be repeated in three dimension, and that gives you at the end a big crystal. We have some slides regarding it. I will show you. But some simple examples we can take to make it more clear. Brick wall. You know that we can build a brick wall. So the basic unit of brick wall is one brick. So if you want to describe the full properties of the bricks, if you understand the primary properties, or if you know the primary properties of brick, one brick, you can define. Just a moment, please. Okay. Hello. Yes, sir. Huh. Okay. Now this is the basic unit of brick wall. Likewise, if you have a crystal, big crystal, there is a small volume unit. So that small volume unit, it seems to us that that small volume unit is only repeated in three dimension, and it has given us a big structure of the crystal. The smallest volume element is called as unit cell. Now this unit cell, if it is repeated in three dimension, we can get a bigger crystal. If you want to understand the structure of a total crystal, you need not have to map the total crystal. So what you have to do is that you have to understand the structure of or arrangement of the atom within that small volume unit. So you can define the properties of a big part of the structure. So the dimensions of the unit cells are described by three axes. We will see that dimensions little late. So to characterize a solid material, you should know that you require many techniques which can be classified according to the uh, interaction of that particular radiation with your material. So we are using photons here in X-ray diffraction. So NMR spectroscopy, ASR, FTIR, this is EXAPS, extended X-ray absorption fine structure. This extended X-ray absorption, near ray spectroscopy, X-ray fluorescence, all uses photons, those interacts with your matter. So you have different types of tool to characterize the material. XRD will tell you about the crystal structure. NMR is element selective. The nucleus of certain elements are NMR active. Certain materials cannot, certain nucleus cannot be probed by NMR, because you need to have some kind of unpaired atomic particles in that particular element so that it can give you an NMR signal. The first and foremost of the technique is the X-ray diffraction. So this technique gives you information on the geometry of the crystal lattice, either it is cubic, monoclinic, tetragonal, something like that. X-ray diffraction will specify the position of the atoms within that small volume unit. So you can get so many properties by using X-ray diffraction technique. That is why this technique is very important to be used to characterize our materials. So when X-rays interact with crystalline substance, one gets a diffraction pattern. We have already seen that X-ray diffraction pattern. We will only repeat these two codes, and then we will start the basic discussion of the crystallography. Every crystalline substance gives a pattern. If your material is crystalline in nature, that has to produce X-ray diffraction pattern. If you take two samples, if you take two samples of same material, for example, if you are taking sodium chloride first sample and second sample. The two samples will always give the same pattern. And in the next experiment, if you will have sodium chloride, if you will have sodium chloride mixed with another material, for example, potassium chloride, if you will mix them together, grind, and if you will make a mixture of this one, and if you will subject this mixture for the powder X-ray diffraction experiment, in a mixture, substances each produces its pattern independently of the others. For example, there will be appearance of XRD pattern of NaCl independent of KCl. KCl will also produce its XRD pattern that cannot be affected by pattern of sodium chloride. So you will get the peaks because of NaCl as well as because of potassium chloride. So this particular observation makes, we can say that, basis for the qualitative analysis of the material, crystalline material, by using XRD tool. So X-ray diffraction pattern of a pure substance is therefore is considered as a fingerprint of that substance. If your XRD pattern is of your pure material, it will be unique for it. If you will take XRD in Pune University or Shivaji University or any other university, same XRD pattern should be visible, produced. So if your material is pure, it should give a unique XRD pattern, so that can stand as a fingerprint of that particular compound. The powder diffraction method is thus suitable for characterization and identification of polycrystalline phases. Okay, somebody has sent me XRD pattern. We will interpret it in the next session. Now we will go towards the discussion, basic discussion of crystalline material. So symmetry is there everywhere in the nature as well as in the synthetic materials. So we will discuss the unit cell first. Now this is the arrangement of atoms within my sample. You can see that this particular motif is there, that is repeated in this direction. So after certain distance there is another atom. If I will go in this direction again, I will meet the next atom. In the similar manner, you can meet after a periodic distance, you can meet an atom in this direction. Same repetition you can observe in this direction too. So the crystalline material is a material in which periodic arrangement of atoms or molecule is there in 3 dimension. So this is a periodic arrangement of atom is there. Now if you want to know the structure of this crystal, you need not have to analyze or solve the structure of all these big particular system. What you have to do is that you have to select a smallest portion of this system. For example, I am selecting it now. So this one. So this seems to be repeated. Now you can see that this is repeated here like a tile we had seen earlierly. This is a repetition. So after each interval of distance, there is a repetition of this pattern. So if you know the structure of this smallest portion, and if you just map it all over the crystal, you will see the crystal structure of all this of this object. Now the smallest unit which is repeating is called a unit cell. A unit cell can be any unit of lattice array which when repeated in all directions, and if it always maintain the same orientation in space, it generates the crystal structure. So to understand the crystal structure, you need to know the structure of smallest volume unit. Now we will make it more clear. Volume unit means it should resemble like a box, then only it is a volume unit. Only plane, if we will consider, plane is a part of volume unit, but it is not completely a volume unit, because plane is in the 2 dimension. Suppose if it is xy plane, it will be only a flat surface. something like this. If you have to consider a smallest volume unit, you need to have a box in which volume is locked. So you can see that this particular box is a smallest volume unit, and if it is repeated in 3 dimension, it will give you a crystal structure. Now, if you consider the smallest unit volume, you need to define the smallest unit volume by 6 parameters. Suppose this is the origin of this volume unit O. You have x direction this side, x direction. Along with b direction, you have along with b axis, you have y direction, and this is the third direction, that is g. Okay. Now you can have same value of or same dimension of A, B, C. And if the angle between A and B is 90 degree, B and C is 90 degree, and C and A is 90 degree, you can get a cube. So you can have different, at least 7 different dimensions for that smallest volume unit. So if you make a smallest volume unit with such a dimension that all the sizes are identical with each other, that is A, dimension of A is same as like dimension of B, as like dimension of C. So if you have 3 dimensions equal with each other, and at the same time the angle between these axes C and B, B and A and C is exactly 90 degree, you can produce a cube. So similarly, you can system 7 types of unit cells. So if you elongate this cube in one direction, suppose that alpha, beta, gamma, so the angle between you can take a system, cubic system, and if you can disturb the cubic system from one side, that you can just change one of the axis, you can elongate it or you can compress it. So you can have tetragonal system. So alpha, beta, gamma angle. So suppose that this is your 3 dimensional system. Suppose this is A, suppose this is a B, suppose this is a C. So the angle between, so this is particularly gamma angle, angle between B axis and A axis. If it is C and A, the angle between C and A will be beta, C and B will be alpha angle. So if these alpha, beta and gamma angles are 90 degree, and if you are changing only one dimension, that is you are keeping A and B identical, and if you are changing C either longer than A or shorter than A, you will get tetragon. You can also change the dimensions of 3 axes. If A is not equal to B is not equal to C, but alpha, beta, gamma angle 90 degree, you can get orthorhomb. You can have A is not equal to B is not equal to C kind of probability. Then alpha, gamma 90 degree, but beta will be non-90. Either it will be smaller or larger than 90 degree slightly. So it will give you monoclinic system. You can get triclinic, in which A is not equal to B is not equal to C, and alpha, beta, gamma are non-90 degree. You have rhombohedral, hexagonal type of system. In rhombohedral, you have A is equal to B is equal to C. Alpha, beta, gamma are also identical with each other, and but their value is not 90 degree. So this system is rhombohedral. Another system you can make with this probability is that hexagonal system. A is equal to B is not equal to C. Alpha, beta 90 degree, gamma is 120 degree. You might have studied all these systems. I am just repeating you just for your sake of convenience. So you should keep in mind 6 parameters are required to define the shape and size of a unit cell. So how, which six parameters are there? I will write here. You require a, you require dimension along b direction, you require dimension of that volume along c direction. So these are the lengths a, b and c are the length parameters. So three cell edge lengths you need to define the volume of the shape, particular unit cell. At the same time, you require the knowledge about alpha, beta, gamma angles between these cell edges. So if you know alpha, beta, gamma value, if you know the value of a, b, c, you can define the dimension of the smallest unit. We call it as a unit cell volume. In the strict mathematical sense, a, b, and c are vectors. So they specify length as well as directions of the system. Okay, forget about the vectors and all. Now you have to only focus on the smallest volume unit. Now you can see that uh, there are seven crystal systems. We have seen that seven crystal systems are there. In this slide, we have seen that there are seven crystal systems. Which one? Cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, hexagonal. So this crystal system can be identified based on the values of A, B, C and alpha, beta, gamma. For example, if our system will have A dimension is equal to B is equal to C, and if the angle alpha, beta, gamma are 90 degree, we can understand that our system is cubic system. Okay. Now, now these seven crystal systems can be further classified into 14 different ways. For example, you have a cube. You have a cube, and if the atom of your material is only located at the corner of that cube, you can say that this is a cube and atoms are only located on the corners of this cube, then you can call it as a simple cube or primitive cube. When the corners of the cubes are occupied by the atoms in the material, you can call it as a simple cubic material, or you can call it as a primitive cube. Now you can see that in the second image, you can see the same cube is there, but in addition to corner atom, these are the red are the corner atoms. In addition to the corner atoms, there is one more atom that is centered at or located at center of the each face. You can see that six faces are there to the cube. 1, 2, 3, 4. This one is a 5, 6. So six faces are there to the cube, and at the center of each face there is a one atom located. So we call it as face centered cube. So face centered cube will have one atom at the corner, at the same time one more atom at the center of the face located. So we call this kind of system as a face centered cube. System is cubic, but the atomic arrangement makes it face centered cube. So another system you can generate from this particular cubic lattice. So you have the corner atom located on the, we can say, corners of each of these corners of the cube. You have atom located over there. In addition to that, at the center of body of the cube, there is one more atom located. So you call it as a body centered cube. Similarly, you can have three tetragons, simple tetragon, body centered tetragon, two tetragons are there, hexagon is there, four orthorhomбs are there, simple orthorhomb, body centered orthorhomb. This is a base centered orthorhomb, face centered orthorhomb. So you can generate total 14 Brevis lattices from 7 crystal systems. Today's lecture will be focused on these three systems. At the end, you will be able to calculate the dimension ABC. You will be able to calculate the volume of this by using XRD, and you will be able to determine the density of material by using XRD pattern at the end of this lecture. Okay. Now this is in short, we have discussed crystal systems. So now we will go to the discussion of planes present in the crystal. We have seen that in the crystal, atoms can occupy at the corner positions. Similarly, they can occupy the centers of the faces. They can occupy center of the body. They can also occupy the center of the edges of the cell. Now, Miller indices. Miller planes are the imaginary planes. So, crystal planes are used to describe the structure of crystals, and crystal planes were used by Bragg to explain the diffraction pattern. Now, when we deduce Bragg's law, we will see what is meant by a plane of atom. Crystal planes are defined by the intercepts. Now, suppose this is a particular unit cell. So, this is unit cell. Origin is here. This is A direction. This is B direction. This is C direction. X, Y, Z. You can either call it as. Now, you can see that this particular shaded, gray shaded area or object is a plane, crystal plane. It makes intercept. So this plane make intercept along A axis at one half A, one half A. This plane make intercept along B axis at one half B, and this plane intersects C axis at 1 C. So you can write the coordinates of intercept of this plane made to the edges of this unit cell. So this side it is one half A, intercept of this plane or intercept made by this plane on the crystal axis is one half A. Second will be similarly one half B, and there will be one C. Sorry, I will write it here, one C. So now what you have to do is that crystal planes are used to describe the crystal structures. The crystal planes are defined by the intercepts they make on the crystal axis. Now, if you want to define this crystal plane, this shaded region, so what you have to do is that you have to first of all find out the intercept this plane can make along ABC axis. So this is one half A, this is one half B, this is one C. Then the inverse of these fractions you have to take. So you have to take inverse of these three coordinates. So inverse of one half is 2. Inverse of this one half will be 2, and inverse of 1 will be 1. So now this inverse of the intercept will be Miller indice of that plane, 2 to 1. So this plane will be 2 to 1 plane. This is very easily you can find out. What you have to do is that first of all you have to find out the origin of, you can consider this figure C. Now we will understand the intercept first. So this is the plane. This plane is cutting A axis at one half A, means the intercept of this plane, the intercept of the plane made at A axis is one half A. B axis is this side. So this plane never cut B axis. It is parallel to B. So the coordinate of intercept will be infinity. Similarly, this plane, you can see that, is parallel to the C axis. So the intercept made by this plane to the C axis is also infinity. So the procedure is that you have to find out the coordinate of intercept. So you have one half A, then B coordinate is infinity, C coordinate is infinity, and then you have to take reciprocal. Reciprocal of this will be something like this, 2 infinity, 1 upon infinity is almost 0, 1 upon infinity is almost 0. So the Miller indice of this plane will be 200. You can see that it is written over here. Now you can choose any dimension. Now we will just take an example that is narrated in the figure E. So this is the origin of the particular unit cell. This is A axis, this is B axis, this is C axis. And this gray surface is nothing but the crystal plane. This crystal plane is intersecting A, B, C axis. The point of the coordinates at the point of intercept, you can see that 1A, 1B, 1C. So you have 1A, you have 1B, you have 1C. Now what you have to do is that you have to take reciprocal of it. So it will be 1, 1, 1. So this plane will nothing but the 1, 1, 1 plane. So what you can understand from these planes? You can understand if somebody will say that there is a crystal plane having HKL value, Miller indice value. These are the HKL value 1, 1, 1. So if you will say that there is a plane in the crystal and it has an indice of 1, 1, 1. It means that that crystal plane is intersecting your A axis at 1A, B axis at 1B and C axis at 1C. Now we will only take one example just to make it very clear. What this particular value 111 will designate or denote us. You can consider this figure B. So this is a figure B. You can consider this corner figure. This gray shaded area is a crystal plane. So it is cutting your A axis at 1/3 A. It is cutting your B axis at 1. Just a moment, please. Hold. Hello, sir. Lecture. Huh? हाँ. थोड्या वेळाने कॉल करतो. Okay. Okay, you consider this particular axis. Okay, crystal plane which is cutting A axis at 1/3 A, which is also cutting B axis at 1/2 B, and cutting C axis at 1/4 C. If you will take the reciprocal of these coordinates, you will have 3, 2, 4 HKL values. So this is a Miller indice of this plane. You can understand from these values that the Miller indices having larger values are spaced near to the origin, and the indice or the planes which are having smaller indices 1, 1, 1 like this one are placed or spaced away from the origin of the unit cell. This information you can get. Now we will go to discuss very fundamental property, that is the we will just understand the packing system. So if you are having face centered cubic crystal type, so you can find out. So this is a face centered cubic in system. This is a face of a cube. You can see that there is one atom located at the corner. So there are 4 corners at this side, so 4 atoms are located. So at the center of this particular face, there is one more atom of the same kind. You just forget about these atoms at this moment. Now, if you want to calculate the part of how much is the contribution of this atom to this unit cell. So each atom that is centered at the corner, that will be 1/8 part of this unit cell, 1/8 part. So this particular atom will contribute its 1/8 part to this unit cell. If your atom is located at the edge, you can say that will have its own 4th part belonging to this unit cell. If your unit cell will have the atom located on the face, that will have its 1/2 part belongings of this particular unit cell. And if your unit cell will contain body centered atom, that will be the total part of that unit cell. We will discuss that little late. Now it is time to discuss the nature of X-rays, how to generate it. and what are the interactions these X-rays will have with your material. So first of all, we will see some basic information regarding X-rays. Can somebody tell me why we need to use the X-rays for this experiment, and why not other radiations, such as why can't we use UV visible light? Why cannot we use IR or ultraviolet light to study the crystal structure of material? Can somebody answer this question? Yes, why we use X-rays, and why not the other radiations to map the crystals? Okay, the answer is that you can see that in crystal, the typical interatomic distance is ranging in the 2 to 3 angstrom unit. In the crystal, or bond distances, or the distance between two atoms when they are closely packed, will be in the range of 2 to 3 angstrom. So it is suitable. X-ray is the suitable radiation for the diffraction study of the crystal. Now you can see that if you are using visible light, so the distance, the wavelength of visible light will be in the nanometric range. So you cannot map the interatomic distances accurately. That is why we have to use X-rays to map the crystal structure. So X-rays are the electromagnetic radiations. What do you mean by electromagnetic radiation? Because when light wave will pass in the medium, it will uh, be associated with electric as well as magnetic component of it. So there will be a electric component that will oscillate mutually perpendicular with the magnetic component of the radiation. The X-rays are used for the investigation of crystal structure because of the shortest wavelength they possess. Similar like X-rays, you can also diffract neutrons and electrons from your material. So neutron diffraction is one more technique that can be used to understand the crystal structure of your system. Secondly, you can use electrons. TEM. In TEM, you will have SAED pattern, selective area electron diffraction pattern. So that is electron diffraction experiment. Okay, the motto of the experiments using neutrons and electrons as a source of diffraction is the same as like X-rays, but they are complementary with each other. Neutron diffraction is especially useful for studying the magnetic ordering in materials, or when your material will have weak scatterers like hydrogen, lithium, then you have to use neutron as a probe to diffract from your material. If the wavelength is of the order of the lattice spacing, then diffraction effects will be prominent. So you have to choose the smallest wavelengths for the experiment. Now we will first of all see how to generate X-rays. You can generate X-rays by different sources. For example, you can have the laboratory tubes, or you can have synchrotron sources. Synchrotron sources are the special sources wherein, if you know the classical physics, the certain laws of classical physics states that if your charged particle, for electron, if you for example, if you take an electron is negatively charged particle. If you make electron beam and if you accelerate it from one end to other end, it will change its velocity continuously. That is, it is its acceleration if you are making. So accelerated electrons will produce a light, or it will change its direction. That is also acceleration. So you can produce a beam of light, and that beam of light falls in the range of different wavelength. So based on the magnet used to bend this electron beam, you can generate X-rays. So that is different story. We will not discuss synchrotron X-rays in this particular topic. We will discuss simple source, laboratory X-ray source in this particular session. X-rays can be generated by decelerating the electrons. X-rays are generated by bombarding a target. This is a target, we call it as anode material. So anions are negatively charged. So anode is positively charged. Now we can see that. So this particular anode is made up of copper in this particular tube. So X-rays are generated by bombarding a copper target or anode by electron beam. Now how to bombard this target by electron beam, I will tell you. So this particular is a glass tube. This is a glass tube, or you can take a quartz tube. So this is glass tube. So this glass tube is sealed. So before sealing, you can introduce a cathode. So this is a tungsten filament. Tungsten filament wire is introduced in it. So anode is made. So this copper metal block is used as anode. This is cathode is negatively charged. So positive ions will be attracted towards cathode. Negative ions will be attracted towards anode. Anode is positively charged. Now you can see that this is a tungsten wire. This is made as anode. Sorry, cathode. Copper metal block is made as anode. Now if you seal this particular tube along with evacuation, it will remove out all the gas from the tube by vacuum pump, and if you seal this tube, we can have a system which is present in a vacuum. You have cathode, you have anode. Now if you connect this cathode and anode to the external circuit, what you have to do is that before connecting it, you have to maintain the potential difference between this particular anode and cathode. So you can maintain potential difference. For example, you can maintain 40,000 volt difference between cathode and anode. And if you pass the electricity through this circuit, what will happen? The electrons will flow this direction. They will reach at this particular cathode, and the surface of the cathode will be saturated with electrons, negatively charged electrons. So electrons will move in this direction. They will saturate the surface of this cathode. Now you have already applied 40,000 volt difference between cathode and anode. Anode is positively charged material, and it will drag the electrons that those are negatively charged towards it. So electrons will move fast. So because of this applied potential between cathode and anode, 40,000 kilovolt or 30,000 kilovolt, based on the setting of the instrument, electrons will be attracted towards the anode. Electrons will be attaining a speed of 1/10 speed of light. So electron at this voltage difference, electron will attain the 1/10 speed of light, and they will strike on the surface of this copper or the anode material. Generally, you can use different material to make anode. So first of all, the common choice is copper. If you have special region, you can choose either cobalt or you can choose molybdenum. Wavelength will be different. We will see how the wavelength will be different in next slide. Now you can see that electrons are accelerated from this cathode towards the anode. Electrons will take speed of 1/10 speed of the light, and they will strike on the surface of anode. So on the anode surface, there will be two different incidents will happen. First of all, electrons are now in motion. They will be stopped on the surface of this particular anode. So electrons will get a break. So it is a common phenomenon when you are driving a vehicle and you are driving it with a speed of 100 kilometer per hour, and suddenly it will put a brake. So there will be, we can say that, sparking. So tire will have some interaction with the surface of the road, and you can see some sparking at the interface. Similarly, when electrons strike the surface of anode, electrons will experience a break. And you can see that classical physics, when electrons will be accelerated, it means that when it changes its speed or when it changes its direction, it emits the any charged particle, free charged particle. When it is accelerated or decelerated, it has to emit the light. Similarly, this electron when get break on the surface of anode, it will emit the X-rays. So this is called as a bremsstrahlung, because this is a phenomenon similar like a sparking of the uh, resulted from the tire surface. So first type of X-rays will be emitted, we call it as a bremsstrahlung. The second event will also happen on the particular surface of this anode. In the second event, so suppose that many thousand electrons are moving from cathode to anode. So out of 100 electron, only one electron is capable. So if 100 electrons are moving from this to this side, out of 100, one electron will be successful in getting penetrated in the atom of this anode material. Now you can see that anode is made up of copper. Now this out of 100, one electron will be penetrated in the copper atom. Now in copper atom, what is the atomic structure? There is a nucleus. So around a nucleus there is one S cell, we call it as a K shell. So after that L cell or second cell will be there. Then there will be third cell, M shell will be there. Now this electron, whatever it is there, that will take out the electron from 1s level of copper atom. So what is the fraction? So out of 100, only one electron will be successful in taking out the electron from K shell of this target or anode material. Now what will happen? The atom of anode material will become destabilized. This atom will have vacancy in its core level, K shell. The atom will be destabilized because its electronic structure is abnormal now. Because so this electron is taking out this electron along with it, and there is a vacancy generated at the core. Now, in order to get stabilized, one of the electron, you can see that there is a next orbital adjacent to 1s is a second s. S to S transition is not allowed. Now, the other orbital, 2p orbitals are there, 2p 1 half and 2p 3 half. These are the two energy levels present in a p. So, either one of these electron will jump down to fulfill this vacancy. This vacancy is removed by getting an electron from the outer shell. So, one of the electron from outer shell will jump down to the K shell and it will fulfill this vacancy. Now you can see that the energy of the electron near to the nucleus is smaller. The electrons which are placed away from nucleus are having higher energy. So the higher or extra energy associated with this electron is given out in terms of light. So this light is in the region of X-ray. So this light we are using for our experiment. So the extra energy associated with 2p or 3p electron, 2p or 3p electron is given out in the form of X-rays. Now you can see that if the electron is jumping from second p orbital having 1/2 energy level, this one, the specific energy will be emitted because that the energy difference. So energy of the electron in 1s and energy of the electron present in the L to 2p by 1 by 2. So this energy difference, for example, you can write it here, delta E is nothing but the h nu, that is the wavelength of the X-rays, is equal to E2 minus E1. So the X-rays emitted from the event will be having energy delta E. So similarly, you have the electron that will jump from third cell to the first cell. You can have E3 minus E1 then. The energy will be very high. If energy is high, means wavelength will be shorter. But this event probability will be smaller, means intensity will be smaller. Out of, if 10 events will happen, out of 10, only one event will be there in which electron from third cell will jump down to the first cell. Otherwise, electron from alpha 1 and alpha 2 will. So in this event also, alpha 1 and alpha 2. So in 100 jumps, sorry, in 150 jumps, 100 jumps will be from this to this. That is 2p 3 by 2 to 1s. 100 and 50 times there will be jump from 2p 1 by 2 to 1s. So this ratio of k alpha 1 and alpha 2 will be 100s to 50, 2s to 1. So more intense beam will be k alpha 1. So we generally have to choose this intense light for the X-ray diffraction experiments. So this line, whatever it is there, this is a line emission, so it is a monochromatic line. So we can use it for the X-ray diffraction. You can see that wavelength, those are k alpha 1 and k alpha 2, they are closely spaced, so larger difference will not be there. But k beta and k alpha, this is termed as k beta. 3p2 1s is k beta, 2p2 1s is k alpha. Now energy of k alpha and k beta is different, but the intensity of k beta is smaller, wavelength is smaller, and intensity will be shorter. Similarly, k alpha 1 and k alpha 2, among k alpha 1 and k alpha 2, k alpha 1 is brilliant, intense peak. So you can see that when you use this kind of instrument to generate the X-rays, this is a X-ray tube, copper X-ray tube we call it, because copper is placed as anode or one of the target material. If you analyze wavelength and intensity of these X-rays emitted out of this particular tube, you will get this kind of profile. So this is a wavelength. So you can just measure the photons of each wavelength emitted from that tube. You will get this kind of profile or spectrum emitted. So this white radiation is because of bremsstrahlung. So bremsstrahlung will give you this kind of emission. This is a emission because of the second event, in which the speedy electron is successfully penetrating copper atom and removing one s electron, and that one s electron is vacancy is fulfilled either by 2p1 by 2 or 2p3 by 2 or 3p cell electron. So you get line emission. So k beta radiation is also intense as compared to this white radiation. Similarly, K alpha radiation is there, which is having more intensity but longer wavelength than the K beta. But we generally choose this K alpha radiation for our experiment. K beta radiation is removed by using metallic filters. For example, if you are using copper anode in your X-ray tube, wavelength of emission will be 1.54. 1 point, I think this is for the molybdenum, I guess. Okay, it is for molybdenum. So for molybdenum, you can see that 0.71 is the K alpha wavelength. So this will be 0.71. If you will have, instead of molybdenum, if you will have copper, this lambda max will appear somewhere here, 1.54. Similarly, you can have different target materials, anode materials. If you use molybdenum, the wavelength of K alpha line will be 0.71 angstrom. It is 1.54 angstrom for copper. For cobalt, it is 1.79 angstrom. For iron, it is 1.94. For chromium, it is 2.29 angstrom. Generally, either copper is generally used X-ray tube anode material. In some cases, cobalt is also used where longer wavelengths are used. Molybdenum is also used in single crystal X-ray diffraction machine. Okay. Now, I hope that all of you understood what is the crystal system, how many crystal systems are there, so how X-rays are produced. Now, we have to use X-rays. We have to use X-rays having single wavelength for our experiment. So, we will choose this K alpha line because it is very intense source of X-rays, and we will direct it to our sample. Now, if you want to use K alpha line, you have to remove this background white spectrum as well as K beta line. So if you are using copper, anode here, you can remove that white spectrum and beta radiation by using nickel filter. So you have to make a metal foil of nickel and you have to put it into the incident beam path. So this nickel foil will absorb copper K beta radiation. So this radiation it will absorb this one, and it will only pass to your sample K alpha radiation. Similarly, you can use for molybdenum, you can use zirconium filter. So for cobalt, you can use iron. So you might have now understood that whatever element is used for anode, you have to go back one atomic number and you have to choose that metal to make the beta filter, so that you can only direct K alpha lines to your sample. Okay. Now we understood the crystal systems. Now we understood the production of X-rays and taking out K alpha lines selectively out of the copper X-ray tube. Now we will see what kind of, when we impinge this X-ray beam of monochromatic wavelength on our sample, what kind of interaction this sample and X-rays will have. We will see in this particular slide. When X-rays hit a specimen, the interaction can result in various signals, emission effects. Okay, the X-ray diffraction. In X-ray diffraction, there is a coherent elastic scattering of X-rays from the electrons present in your sample. Now you can see that this is your sample. These are the incident X-rays upon it. If the specimen will absorb the X-rays, it will get heated up. So X-ray energy will be utilized to hit the sample atoms. So heat will be generated. This is one phenomenon. Suppose that incident X-rays are absorbed and if they are scattered back, you can have two types of scattering. You can have elastic scattering as well as inelastic scattering. Now, for X-ray diffraction, the incident X-rays are fall on the specimen. The specimen will absorb these X-rays and they will scatter this X-ray with the same wavelength. So we call it as a coherent elastic scattering. The X-ray diffraction is nothing but the coherent elastic scattering of the X-rays from the electrons present in your sample atoms. Okay, now we will see. We shall consider the important topic as to how X-rays interact with a crystalline array of atoms to give rise to the phenomenon known as X-ray diffraction. Now you have to consider X-ray diffraction. Before that, you have to only keep in mind diffraction requires three important conditions to be satisfied. If X-rays have to get diffracted from your sample, your X-ray beam has to follow these three conditions. First condition, which one? It should scatter, it should be scattered from your material coherently. So it should produce the same wavelength before incident. And X-rays, those reach your sample should be parallel to each other. What it says, the wavelength of the X-rays scattered and incident on your sample should be same. So elastic scattering should be there. The X-ray beam, whatever you are using, that should be made up of a single wavelength, and whatever X-rays reach your sample should be a parallel beam or parallel wave of X-rays. Okay. Now we will go to the X-ray diffraction experiment. So we have to now prove the Bragg's law. Okay, this is the picture of X-ray tube, and you can see that this is a glass tube in which copper anode is sealed. This is a cathode. It is a cup shaped cathode in which filament of tungsten is there. So this is a evacuated tube. So from the back side of the anode, you can circulate the water. We call it as a chilling system. So the electrons will jump from this cathode and they will bombard on the surface of the anode. So anode surface will get heated up. To cool these anode surface, you need to circulate the chilled water from the back surface of this particular anode. So chiller is required in X-ray diffraction. Now you can see that whatever X-rays are produced in this tube, those are taken out here. This is X-ray source. These X-rays are taken to your sample by using different sorts of slits, and it is allowed to fall on your sample. Now we will see. So slits, these are the slits which are of different dimensions. Those are used to fall on your sample. So you can define the surface of your sample, how much surface of your sample can be illuminated is determined by putting this kind of optics in the incident beam path. So this is slit, this is mask. So solar slit is used. So this is your source here. The X-rays are passed through this divergent slit and then they are passed through solar slits which make the X-ray beam parallel to each other. So we want the X-rays monochromatic, then we want X-rays parallel to each other, and at last these X-rays should fall on your material and they should not change the wavelength. They should retain their wavelength. So likewise. So now X-ray diffraction is a phenomenon. It is a constructive interference of two waves or more than two waves. So now we will just forget about it. We will come back to this one. We will first of all deduce the Bragg's law and then we will take small break. Okay, now we will deduce the Bragg's law here. So you can see that we have already seen this system, crystal system. So there are atomic planes present in the crystal. So we have calculated their Miller indices. Suppose this is the first layer of atoms present in a crystal. And this is the second layer of atoms present in a crystal. So these two planes are parallel to each other. These two planes are parallel to each other. Now there are now for X-ray diffraction we need to use X-ray beam which is having parallel rays in it. So this is the first beam of X-ray and this is the second beam of X-ray. These two X-ray beams are parallel to each other. Now you can see that. Imagine a Bragg's diffraction as a reflection of X-rays on the surface of atomic planes in the crystal lattice. Actually, X-ray diffraction is nothing but the reflection of X-rays. X-ray diffraction is nothing but the reflection of X-rays. In reflection of light, you can see that if light is falling on the surface of a mirror and if it is reflected, the angle of incidence, this angle is equal to angle of scattering. So angle of incidence is equal to angle of reflectance. So these two angles are identical. That is why these two angles. This is the first layer of the atom or first plane of the atom. This is second plane of the atom. Now you can see that these two planes are parallel to each other. First beam travels to the point O. At point O there is one atom. So first beam strike on the atom placed at point O and it is reflected from this point O. Okay. Now second beam is there. So angle of incidence is equal to angle of reflection. We made it here. Due to the repetitive nature of the crystal, we have already said that in the crystalline material there is a repetitive arrangement of the atom is there. So because of this repetitive arrangement of the atom, these planes would be separated by a constant distance d. This means that there will be a third layer of atom here somewhere. And the distance between first and second layer will be same as like second and third layer. So there will be fourth layer of atom somewhere here. So due to the repetitive nature of the crystal, the planes would be separated by a constant distance and they will be repeated in this direction. Okay. Now the two X-ray beams of wavelength, same wavelength, monochromatic, lambda, arrive in phase. You can see that. So it is like a wavefront. So these two waves will reach to this point. So up to this point, the wavefront is formed. Till this wavefront is maintained by these two beams up to this point. You can see that. The first beam, the two X-ray beams of wavelength lambda arrive in phase. In phase means you should know that the crest and trough of both the waves will resemble the same. This is the first beam, this is the second beam. The crest will be superimposing of the second wave will be superimposed on the first wave. Similarly, trough will do the same. So the first and second beam will be starting from the same lamp, same source. They are parallel to each other. So now what we can understand is that these two waves will be in phase with each other up to this point OE. Up to the wavefront OE, these two waves will be in phase with each other. You can see that. Two X-ray beams of wavelength lambda arrive in phase onto the respective imaginary planes with an angle of incidence theta and form a wavefront. So these two waves form a wavefront up to this particular line. In order to obtain a cooperative effect, for example, diffraction is a reflection, but diffraction is a constructive interference of two waves. You can see that this is the first beam, this is the second beam. So crest of first beam will superimpose with the crest of second beam. Trough of first beam will superimpose with the trough of second beam. When you add these two waves together, you will get constructive interference. So intensity of the resulting wave will be enhanced. This, at the other hand, if first wave and second wave will be out of phase, for example, crest is superimposing on the second uh, trough of second wave, so these waves will cancel. When you add these two waves together, these two waves will cancel with each other, and you will see nothing. So dark point will be observed. So this is kind of destructive interference. X-ray diffraction is constructive interference of the two waves. Those are scattered from the adjacent layers of the atoms. That is parallel planes of the atoms present in the crystal. So in order to maintain that constructive interference, after reflection, so up to this point we don't have any problem. The first wave is scattered with angle, same angle theta, so angle of reflectance, incidence is equal to angle of reflectance. Now the second beam is here, it doesn't get any atom to get interacted, so it has to travel extra distance E to G. So it gets, or it meets the atom from which it gets scattered. suppose that it is also Suppose that it is also reflected from this point, it will make angle of reflection theta. So this will be reflected in this direction GH. Now it will travel extra distance of EG plus GH. Second wave will travel extra distance of EG plus GH. And after traveling this extra distance, if this wave should have to form constructive interference with first beam. So the phase difference, that is this particular distance traveled by the second wave, should be multiple, integral multiple of full wavelength. So this should be either one wave or two wave or three wave, this EG plus GH. So in order to obtain a cooperative effect, after reflection, both X-ray beams should be present in the same phase, a situation that will only happen if the difference of the distance, or if the path difference traveled by the wave front OF, this OF and OH corresponds with an integer multiple of wavelength. So the second wave will have to travel extra distance EG, oh sorry, this is F, FG plus GH. This FG plus GH is extra distance traveled by the second wave. That extra distance should be integral multiple of the wavelength. So then and then only the second wave will be in phase with the first wave, and then constructive interference will be observed. So this condition is equivalent to say that sum of the FG, so this distance, plus GH, this distance, corresponds to an integer, that is n, 1 2 3 times the wavelength. So Fg plus Gh is equal to n lambda. Now Fg is equal to Gh by trigonometry. Now you can see that this is also angle theta, this is 90 degree. So you have to find out these angles. So this angle will be theta, this will be 90 minus theta here, this will be 90 minus theta, 90, and this will be theta. So this angle is equal to this one. So if you want to determine the distance of EFG and GH, what you can do, you can use a trigonometry, you can take a sine theta. So sine theta will be FG upon this OG. So FG upon OG, OG is nothing but the D, it is interplanar distance. So you can write sine theta is equal to Fg upon OG. OG is nothing but the D. So sine theta will be Fg upon D. So you take this D this side. So Fg will be D sine theta. Fg is equal to Gh. Now Fg is equal to D sine theta. Gh will be D sine theta. So you put the values in this equation. Fg D sine theta plus D sine theta will be n lambda. So you will have 2D sine theta is equal to n lambda. So this is a simple deduction of Bragg's law, n lambda. Now in this equation, 2 is, we can say that real number. This is a D is nothing but the distance between two planes of atom. We call it as the interplanar distance. Sine theta. This theta is nothing but the angle of incidence. Lambda is the wavelength of the X-rays that you are using for the experiment. You are using monochromatic X-rays. So wavelength will be having only one value. So n is always 1. It is order of reflection. First order reflections are only seen many times. Only in rare condition, second order reflections are visible. But for your powder X-ray diffraction, you never see the second order reflection. So n will be always 1. So lambda is equal to 2D sine theta. You will get in this situation. Lambda is equal to 2D sine theta. So lambda is known because you know the anode material. If you have anode copper, so wavelength will be 1.54. So you understand lambda value. Theta is the angle of incidence. So if you measure this angle of incidence, this can be measured by using goniometer. So you can have the source, you can have your sample, and you can allow the X-rays from source to fall on your sample, and you can just incline your sample position at different angles. So like titration, we make a titration, we do titrations of acid and bases. So we add the volume of acid either or base, 1 ml, 2 ml, 3 ml likewise. So you can change the angle 10, 10.2, 10.4, 10.6, 10.8 in controllable manner, that with the help of goniometer. So angle can be controlled. So you can have control over the angle of incidence. So if you know the angle at which reflection appears, you can measure the D value at that particular condition. Okay, now we'll just see this difference between reflection and diffraction, and then we'll stop for 5-10 minutes and then we'll start. Though the diffraction, you can see that diffraction is nothing but the reflection. So diffraction has been visualized as a reflection from a set of planes. Diffraction is nothing but the reflection, but this reflection takes place through number of planes. First plane, second plane, third plane, fourth plane. All crystal planes will take part in the diffraction. So it is a bulk reflection. Diffraction is nothing but the reflection from bulk planes. And reflection is a surface phenomenon. Simple reflection of light is nothing but the reflection from the first plane. But diffraction occurs throughout the planes which are just embedded below the surface layers of the atom. Reflection can take place at any angle. Diffraction can only take place at the Bragg angles. For example, if your material is there, your material will have limited number of d values. D is nothing but the distance between two atomic layers. So if your D is having limited number, suppose your layers are having 4 different values. So you at 4 different times you can satisfy this condition. It means that at these 4 different conditions only you can get diffraction conditions or diffraction law satisfied. So reflection can take place at any angle, but diffraction can take place at only Bragg angles. 100% of the intensity that falls on the surface of the mirror will be reflected. For diffraction, only the fraction of the light incident on the sample will be diffracted. So this is the difference between reflection and diffraction. Now, I will just summarize this particular session. So you can keep in mind Bragg's law is 2d sine theta is equal to n lambda, where d is the property of your solid. D is the property of the solid. Theta can be controlled by using goniometer. N will always have value of 1. Lambda is a wavelength that is known for the experiment. So if you know the source of X-rays, you will have in your hand the value of lambda. So this side will be constant. So if you will change value of theta, you can probe different D values present in your material. Okay, now for the crystallography, you should know that there are 7 crystal systems. So in 7 crystal systems, for today's session, we will be considering only cube. For cube is the smallest volume in it. It has 6 parameters that can define its dimension. So you have 3 different edges A, B, C, which are equal to each other, and the angle between these A, B, C are always 90 degree alpha, beta, gamma. So now we will use these two equations. 2d sine theta is equal to n lambda, and there will be one more equation that we will just take from the concept of reciprocal lattice is there. We will just consider one equation from that particular concept, and we will mix this Bragg's equation with that one, and we will determine so many properties of the unit cell consecutively. So is there any query for this session? If anybody want to ask some queries, they are free to discuss. So we will have break of 10 minutes and then we will join here. In the next session, we will use these two equations. One, n is equal to n lambda is equal to 2d sine theta. Second equation that we will use is 1 over d is equal to a square plus k square plus l square upon a square. So that is the equation that is resulting from the reciprocal lattice concept. So common in these two equations is a d. So we will use mix these two equations and then we will solve. We will calculate the lattice parameters A, B, C. We will calculate lattice volume. We will calculate lattice density. Then we will determine the lattice constant A. Then we will determine the system, either primitive cube, face centered cube, or body centered cube. Okay, is there any?
Participants are requested to put your questions in question answer section or chat box. If
Yeah,
you have,
otherwise they can just talk on the meeting also.
yes.
Yeah. I think there is no question from the students either. From this I can only understand that everybody understand everything, and otherwise everybody understand nothing. Okay, no problem. This is the only fundamental discussion. So you can only keep in mind that equation n lambda is equal to 2d sine theta. That is the law of diffraction, and that is the only equation that will give us large sorts of information about our system that we will solve in the next lecture. I think after 10 minutes we can join here. Yes.
Yes, sir.
Okay, sir. Thank you.
The session will restart after 10 minutes.